All right.
Let's see now. There's a problem we started last time. And very quickly it had this box here, hanging up, being suspended by 4 ropes. And basically, can somebody read off, I'm sure you guys all did this, what were the 4 vectors describing these positions where it's attached? You know which one? Oh, it's about, sorry, 1 second.
They're not vectors.
The points.
I know. Well, the first thing I asked you to do yesterday was to make the vectors that represent those. Which one was it? Number 62?
Yeah. 62, 11, 22.
Here we go. Yeah. Page 702.
That's all they want to know is those vectors.
They want to know the forces. I can talk about the position vectors, right? And that doesn't have anything to do with the forces. So this point, we did 1 point the other day. I think we did this point. This was 0, 0, -4. So that vector there would be -2, 0, 4, right? Okay, so the rest of them would just be, there should be a 0, -2, 4. There should be a 2, 0, 4, and a 0, -0. We already got that guy. Okay, cool. So those are just the position vectors, really. How long those cables really are. So they actually have in them inherently directions and all that kind of business and magnitudes. So what I really want to do here, and I kind of gave you that first step, I want to find out some multiple of these. That would be the force piece of this. Because the force vectors are going to point in the same direction, right? If I got a rope and I'm pulling, the force vector is this way, along the rope. So I'm going to use the established direction they gave me with these position vectors I can make, multiply them by I don't know what yet. I don't know how much force each one is applying, right? Some of us realized the setup requires them to each have the same force because they're all equidistant from the crate. How are we doing so far?
Yeah.
Okay, okay. And these have to somehow add up to be the
500.
Yeah, this will be 500 pounds here, right? And that's actually at effectively, well, and it'll be 500, and let's see if somebody can get this. Write that as a vector, though.
0, 0, 500.
Cool. And just to be a little careful, yeah, let's call it -500 since that's down. That kind of makes sense. If you don't call it -500, your forces will be negative. You're just calling up negative. Who cares? Right? Negative in physics is really just directional. How are we doing so far? Is that?
Yeah.
That's basically what's going on here. What's holding this thing up? Those 4 are acting together to counteract this weight. So, what do I get? What do I get when I add these up? I get x times 0, 0, 16. And really, the way I've set this up is not a negative here, because it is negative, but I want it to equal 500 to kind of balance it out. You guys with me? So the negative is just a directional thing. So I want this to equal 0, 0, 500.
Professor,
Yes, sir.
when you add those 4 x's, is it just x or is it 4x?
Well, remember, this is just distributive problem.
Oh.
Right. Just factoring the x out. You guys cool with that? I mean, 4x plus 4x plus 4x plus 4x is 16x. Cool. You guys see that? So if you want to, you can bring the x's in and just go to town, or just leave them out and put it on the outside. Good old distributive problem. Okay, cool. Nah, that's not cool. Sorry. So what do I get here? How can I solve this equation then?
500.
These two are good. 0x is 0. Yay. So the only piece I really need is 16x has to equal 500, which means x must be 500 divided by 16, which reduces to 125 over 4. Is that right? Yes, that sounds right. Good. All right, and then your answer is staring in the face, and your answer is just put 125 over 4 in front of each of these, and you're done.
I thought of it as a different approach. If you take, you need the middle line, the middle vector, which is the component of cosine theta of that thing. So for cosine theta, and you add them together, you will find.
I love it. So again, like I said last time, there's no need to necessarily bring angles in because the vectors
It's
have
not
them.
because it's just the JSON which you basically need over.
I'm with you. And it's not that big of a deal. It shouldn't be difficult. I'm just saying there's no real need to. So that's the other way to do this, is to let's just look at the components. All that matters, the only component that really matters here is the up and down component, right? So I can break it off using the angles. And the angles are simple enough to get because they're just ratios of what they gave me here, right? Which is all trig is ratios of sides of these stupid triangles. All right, but, and to tell you honestly, that's the way I would normally do it because of my physics background, but this is more related to what they want to see, just using pure vectors. Okay, so you guys look very dissatisfied with that. It's too bad. All right. Any other questions from homework somewhere? Any other? Yeah. Oh, cool. Oh, so they kind of, on 54, they give you a multi-step problem because it's a little evil to be giving this problem quite yet without a lot of guidance because we haven't actually talked directly about lines and what they look like, what their formulas look like in different dimensions, which is what we might do today. Yeah, so is there a certain part of this you had trouble with? So 54 specifically says they want to find out the distance between this point, 0 to 6, and this line, L, having the direction where'd it go? 3, 0, negative 4. And they told you, now there's the key part. This line goes through the origin. That's what it says. Because otherwise, to really get a line, I need to know a point it goes through in a direction, right? That's what we need to get a line. mx plus b, m direction, b point. You use the y-intercept, so you can use x times y dot blah blah. We all know the old story of algebra and getting lines. The cool thing is that extends beautifully to 3, 4, 5 dimensions, which we'll see today. So they step you through this because if you think about this, this is a very difficult problem if they just ask you, how far is that point away from this line? What does that really mean? If I have some line and some point, somehow I need to know what? I mean, what is the distance to that point? What's the key part of figuring out the distance from the line?
So this is perpendicular.
Perpendicular. The idea of perpendicular. Obviously, that's why they threw this into this section, because now with the dot product, what are two things perpendicular? When the dot product is 0, right? So that's kind of like why they wanted to throw this problem in here, because the main idea here is you can't measure distance unless you have something perpendicular. Cool. This is this certain height because I'm going straight down to the floor. You can't say, well, I'm actually 7 feet tall if you go like that. No, Jeff, sorry, I can't play that much basketball. Too bad for you. So this has got to be somehow perpendicular, and we're in 3 dimensions, which makes everything a little bit harder if you try to attack it with the old way of doing things. So was there, part A says, find any vector v. This one is really silly, in direction of L. Okay, so what vector do you think would be a good idea?
3, 0.
Yeah, 3, 0, negative 4, or any multiple thereof, right? Is that cool? So if you don't like 3, 0, negative 4, you can use negative 3, 0, 4. I don't care. When you say in the direction of a line, what's kind of weird about that?
You go either way.
The line goes both ways, so you can use negative multiples, positive multiples, or just leave the poor dude alone. Let's use him. That just makes freaking sense. You've already done part of the work for me. They gave me the vector. Part B says find the position vector u corresponding to P.
You chose the vector 0, 0, 0. That would kind of be cheating, but would it be correct?
The problem with the vector 0, 0, 0, does it by itself define a direction? No. In fact, I told you the book I think says it has no direction, and in a sense it actually has all directions. So that's a poor choice for pointing you in the right direction. All right, can you tell me which way to go? I'm pointing in the direction right now. Well, that's helpful, thanks. You know, so it's not a good choice. Part B is pretty straightforward. It's just maybe some terminology if we're not used to this, but how to get the position vector for this for the vector for that point.
From the origin to the point.
Say again?
Just the vector from the origin to the point.
I love it. Which in this case really just says make the parentheses into brackets, right? I mean, how are we doing so far? I mean, this is part A and B are very easy. It's just in the context of this problem, it might be like, what the hell do they want from me, right? They don't want that much from you there yet. Part C is the first really cool part. Part C is that last thing we did last time. Part C is what's the projection of, which way did they go?
U on V.
I like it. U on V. So really, let me kind of catch us up to what we're doing. We found a vector V in the direction of L. So here's the direction, here's a V in the direction of L. We found the U, here's a point P. You guys with me? If you find the, and of course the way I've drawn this, now what is this U? This is specifically from the origin, right? So what's going to happen when I try to find the projection of U on V? And what we're really trying to do, let me find out, where is this? Oh, here it is. Any vector V in the direction of L, find the position vector U corresponding to V. So, let me make sure I'm with this. So here's the line L. I'm just doing this in 2 dimensions to make it easier to draw. Here's some point P. Here's the position vector. Let me just put that P somewhere. Put it on that. Here's the position vector P. Here is the, because the way I was drawing it, everything was beautifully orthogonal. It didn't have to be. Here's the V. Here's the U. You guys with me? My picture was specifically, they're already orthogonal. Well, that would be nice. So you got to be careful. This is more general. So look what they're going to do here. How can I find this? If I can find this vector, I can just find its length and then I'm done, right? Because that's the vector that's orthogonal to V that points from V to U. That's the distance, right? That's how far away it is. You guys with me?
Yes.
So what they're saying is, we'll first find this stupid thing. And what is that stupid thing? Part C. Now here's the beautiful thing. If you find that component of U, the other component of U, is it on my picture already? The other component of U. Because when I break U into components based on V, here's one component, the other component would be this, which is right there. You guys with me?
Yeah.
So the really cool thing is, once you find a projection, how do you get the other component? Do the U minus the projection. That must be the rest of it. It's almost too easy, because look what they say on part D. Take U minus the projection of V on U. Did you get that in the right way? No, U on V. I don't know why I keep thinking they turn it around. If you take U minus this, you get this, don't you? That is the definition of visual vector subtraction. Don't forget that. It's going to be very useful every now and again in this class to make some problems pretty easy, actually. So part C is find the projection. That's just a formula, right? And part D is find that subtraction. You can do the subtraction. So let's see what's part C look like. What's the formula for the projection? Who can look that up real quick or knows it?
You got V
U dot V.
times vector V over magnitude V squared.
I like it, magnitude V squared. In the book you'll see sometimes they have V dot V, it doesn't matter. They're both the same thing. Okay. Maybe.
And we just
And
use,
now you just plug in what we know.
we just use that V that you already have written.
Yeah, we got the V, we've got the U. This is not even, you know, you have to work with variables only. You have the numbers, you have the vector components. You can just throw them in. What's U dot V gonna be? Yeah, 0, 0, negative 24. Right, you can find the length of V. In fact, that should be easy. 3, 4, 5, right? Because the middle is 0, so that's awesome. 3, 4, 5 triangle, I love it. So the length of V is 5, so that's 5 squared. So you get negative 24 over 5, well 5, sorry. The length of V is, no, it's 5 squared, yes. Times V, which is 3, 0, negative 4. So that's part C. So what you did there was you found this piece. Part D makes you find this piece, and then what do you think part E is going to do? You want the distance, so if you find the vector, you find its magnitude. Ooh, and part E finds the magnitude. Ooh, we can kind of see where they're going now with this, right? I would not expect any of us to be able to come up with those steps on your own. But tease out why the hell the steps work. Why do they get you to where you want to be? There's the picture. There's what each step is doing. Each step is doing. I want to get this damn thing, and that's how you get it. Okay. But something on the surface, it sounds very simple. How far is this point from this line? It's not exactly that simple, right? There's a little more involved when you start getting the higher dimensions. Okay. So hopefully that's enough to carry you through to the end. Now it's just a bunch of plug and shove. Was there any specific question that I didn't address? Or is that okay to get you going? Okay. All right, any other questions? Comments? No? I think we finished 11.3. Oh, one last thing I didn't really talk about directly. I hate, well, let me not say that. The projection of U on V, like we have over there. So if you remember, we kind of got here by
That's multiplied by U, right?
doing this here. Well, U on V, so UV, V squared V. And actually going way back in time, way back to the beginning of our derivation. I don't know if you guys remember this, but we had this whole idea of here's U, this is U cosine theta, right? And then I just had to multiply by a vector in the direction of this V. Do you guys remember that?
Yeah.
We started with that's the length that I want, and that's the direction that I want to go in. So this is really, this book makes a big deal of this, which before I never saw this really. Scalar of, I don't know why I keep trying to, U on V. Well, I know why, because I'm not used to writing it backwards. I'm trying to write it backwards to make a point with what's what, and then mess myself up. Scalar of U on V. Because that is a scalar. So when you see them reference this, they're referring just to this, just to that side of the triangle, what you would have done back in pre-calc. Yes?
So the scalar projection is basically it's minus the V vector over V magnitude?
Be careful, don't say scalar projection. The scalar of this, it's not really a projection yet, but the scalar piece of this,
Okay.
do they call it scalar projection?
Well, that was on the quiz that you gave us at the end of class yesterday.
I'm evil. Well, that's better. The scalar component.
Component, sorry.
That's one. The scalar component of
U
this.
on to V.
Yeah, just take out the direction. Right. So back in pre-calc, you would have had this problem. You have an 11-foot ladder landing against a stupid building. Crazy people in their stupid ladder, right? And then they tell you this is 25 degrees, and they say, well, how far away from the building is it? Right, what would that be? And so you've done that before, you just never called it the scalar component of the projection of, just different terminology, but old stuff. That's the length of that side of the triangle. When you add in the directional piece, you've made it a vector. That's the true projection now. That's the projection vector. Okay, how we doing? This isn't overly evil stuff. Yeah. Okay, so I think that was the last piece I really didn't address directly from 11.3. So now we're going to get into 11.4. Being linear creatures. So before I really get into this, what's going to become very important is your ability to work with determinants. And the reason that is because the easiest way to calculate the entity we're going to be talking about in a minute, it's called crossproduct. The easiest way to determine that is to set up a matrix and find its determinant. I got the feeling that a lot of us maybe have never done it, or it's been a long time. Right? So here, let me give you an example of how to calculate a determinant and what use it has, immediate use. You can actually teach determinants back in 103, 110, because they're actually useful for finding solutions to systems of equations. Okay, so those of you taking linear, I think there's a few of you taking linear right now, and maybe it's coming up, you'll be finding solutions to systems of equations and interpreting them geometrically. Yay. That's what the first part of that does. So here's a very simple example of where matrices come into play. So let me just focus on the matrix that describes the problem, not the answers. This matrix, who knows what the matrix for that piece would look like? 1, 1, 1, negative 1. Now 2 by 2 determinant. And see why 2 by 2, 2 rows, 2 columns. Yeah, AD minus BC. So it's very simple for a 2, 2. So here's the idea. This would be 1 times negative 1. You can do it, Joe. Minus 1 times 1. So in general, it's for 2 by 2. It's got to be AD minus BC. So that's the determinant for that matrix. And in this case, what do you get? Yeah, and the key thing there is it doesn't equal, who knows? What's the key number to look for? It doesn't equal 0, which means that this has an answer. Or it could lead to an answer at least. It's not going to be because of a problem with this. It might be because of a problem with this. All right, that's the meaning of that. Let me give you a 3 by 3 example. Here's how it works in 3 dimensions. Or actually, 3 by 3 dimensions. What you need to do is you break it down into 3 2 by 2 problems. And to do that, you pick a row. And we call it, you pick a row or a column to expand around. How many of you guys remember or have heard of this type of thing before? Oh crap, all right, here we go. Because this, I want to spend a lot of time on this, but I'll do it with this ugly thing and then we'll do it with a real problem and show you which row, which column is best to use. So if we just choose ABC, we'll expand around the first row. When you do A, you're going to multiply that by the determinant of everything not in A's row or column. So let me just say that, see what you guys think about that. what elements are not in A's row or column? EFHI, and that just finds a little tiny two-dimensional thing. Or 2x2 matrix. Dimensions get a little freaky with matrices. Yeah.
Did you say you multiplied times the determinant and those letters?
Determinant, yeah, sorry.
Those letters are the determinant?
That's the determinant. And that determinant would be, I keep drawing this wrong things here. The determinant looks more like absolute value symbols. When you put the little spokes on them, that becomes just a matrix. So the absolute value symbols kind of tell you to find the determinant. So what I'm doing is I'm multiplying A as a coefficient in front of that determinant. Now, who remembers what's kind of in the background of this all the time? There's what's called a little checkerboard matrix, which tells you, these are all kind of shortcuts. And I'm going to leave it to linear algebra. If you take it, they're going to prove a lot of what I'm doing right now, that it actually works and gets what you want it to get. I'm just going to show you how the hell it works, because I got to get into my Calc 3 stuff. So that's why this is positive. B, it's got to be minus B times what determinant? What's not in B's row or column? DF, GI. And then C would be plus. And what's not in C's row or column? DEGH. I'm not going to go to the next row, because the next row you just EI minus FH. DI minus GF. Right? Just a little 2x2 matrix determinant, which is a pretty simple, that's this guy. Yes?
Going back to when we started, does it not matter what the equations equal? Because you had the first line equals 7, the second line equal 2.
One level of analyzing systems of equations is independent of what they might equal. Because you can tell if, given equations without their related answers, if it would even possibly have an answer by itself anyway. And what do I mean by that? I mean this. Let's do two different things. Let's do a problem that works and a problem that doesn't, and see what their determinants come out to be. Right? So a problem that would work would be like, maybe actually make it something that would be nice. Cool. I wonder what it could be. You can do it, John.
No y there.
Say again?
The y disappears. Yeah, plus minus.
Yeah, you just make the matrix like you do here, and you just ignore
Yeah, so you could either start attacking this directly and do 1 plus 2 and kill the y, and then do 2 plus 3 and kill the y, right? That whole thing. And the worst part about that problem was organization, bookkeeping. And of course, when I teach it to my math, where do I do this? Math 110, I don't know, where do I do? I don't know. Well, yeah, when you do system of 3 equations, so it's like Math 90 and Math 110 we do this in. The problem they have is remembering what the hell they've already done, and what the hell it means, and where to go from there. They lose track. So if I write the associated, let's just focus on this, because I'm not going to get into solving this equation. That's a whole other thing. We don't care about that. What's the matrix for this look like? 1, 1, 1, because it's just the coefficients.
1, negative 1.
2, 1, 1. Cool. What's the determinant of this? I mean, a good row, it doesn't really matter, but 1, 1, 1 sounds good to me. If there were any zeros, I would obviously pick that row or column, because then I can eliminate that piece, right? So if I do it around 1, so if I do it around this first row, it'd be 1 times negative 1, no, you can do it, Jeff. 1, 1, 1, minus 1 times 1, 1, 2, 1, plus 1 times 1, negative 1, 2, 1. And what's that going to be? What's this little dude here? Negative 1 minus 1, negative 2, 1 minus 2, 1 minus negative 2, so 1 plus 2. You doing all right? Is that cool? And then you get negative 2 plus 1 is negative 1, plus 3 is 2. So it's not 0. So this, as long as these are set up correctly, it could have an answer. It could have an answer. Yes, sir.
Well, what does that 2 mean with reference to what the equation's equal?
We'll get to that. The 2 does have meaning beyond that, but right now I just want to focus on the fact that it's not 0. And really, to tell you honestly, we're not going to be doing solving systems of equations, right? There's no purpose for that really in here. If you take differential equations, you'll be doing stuff with matrices like this. All I need you to do is to be able to calculate a determinant. That's it. If you can do that, you'll be golden here for a while. On cross products, anyway. So what's an example of a 3 by 3 problem that won't work? What won't work, meaning either it's going to have no solution or infinitely many solutions, not just a single solution, right? It's going to be somehow. Yeah, if I had like x plus y plus z equal really, and then 2x plus 2y plus 2z, 2 and 3x plus 3y plus 3z equals 3, right? The problem there is, do I really have 3 separate pieces of information? No, it's the same one repeated 3 times. And if I have 3 unknowns, I need 3 pieces of information. This is not going to be determinant. You can't determine all the answers all the way down. You can only give a bunch of variable answers for it. And that's linear algebra is going to determine, is your answer a plane? Is it a point? Is it a volume? That's what linear algebra does. It actually looks at the geometry of your answer. We're not. This is almost too easy though. I mean, what would the matrix look like for this?
1, 1, 1, 2, 2, 2, 3, 3, 3.
And can you see what's going to happen here? If you expand around this one, you don't have to. I keep doing that because it happens to be the easiest one, but you can do anything. But if you expand around the first one, you get 6 minus 6, 6 minus 6, 6 minus 6 in every single one of them. So it's going to be 0. Which goes along with the idea that this is not going to lead you to a fully determined answer, right? Okay. Sweet. So something else that would work would be if I had, like x plus y plus z, 2x plus 3y plus z, and then 3x plus 4y plus 2z. Can anybody see where that last one came from?
Yeah.
I took those and added them together. So again, that one is dependent on those 2, so it's not a fully described system. I've only got 2 pieces of information, not 3. So it would have, similarly, it would have a 0 determinant if you set that up. All right, how we do? Okay, so do me a favor, bank that for just a couple minutes here. Now let me get into cross product. We'll bring this into play where it becomes useful, and then we'll try some examples out. So really, I have, and again, just to remind you guys, I kind of gave you a little preview. The dot product, the answer to a dot product, the inputs are what? The output is what? Inputs are vectors, the output is scalar. So it had really good physical meaning. We had problems where I had some dude pushing the crate across it. You could actually visualize what was going on. But deeper mathematics say, that's not good. I want to multiply 2 vectors and get a vector. Damn it, that's what I'm used to. Multiply a number, I get a number. Vector, I should get a freaking vector. This only works in R3, and of course by that I mean X, Y, Z. It does work in higher dimensions, but then you start calling them tensor calculus, tensors, which are just higher order matrices. Which again, I'll let you get to if you ever take continuum mechanics. It all depends on what the hell you do. If you're doing engineering, you might be taking it. So that's in your future. It only works in R cubed, right? That's the only place you can really call it a cross product. Okay, how are we doing so far? I mean, I haven't really said anything yet, so we're doing okay. And the nice thing is, I want to point something out that they've already done for us in the book. Let me see if I can. Yeah, let's do it like this. If I had U1 plus U2 plus U3 times V1 plus V2 plus V3, stay with me now. Go with me. This is old news. We can all do this very simply. I'll get U1V1 plus U1V2 plus U1V3 plus U2V1 plus U2V2 plus U2V3 plus U3V1 plus U3V2 plus U3. Okay, that was exciting. What is this, and this? What is U1V1 plus U2V2 plus U3V3?
Dot product.
Dot product. Now, this is not, I really want to make sure you understand this. This is a demonstration of where these things sort of come from. It's not exactly what's really going on here, but it does help me when I first learned this stuff. We've talked about these parts of a multiplication problem. What we haven't used in some way are these cross products. I mean, you've probably heard the term cross product before, just not quite as directly as we're saying. We're saying this is the cross product. But cross product is like foiling, and you get something and it has to go across to the other thing. You guys kind of with me? This U1V1 is not a cross product. It's direct. But when U1 goes to V2, that's a cross product. It's not a cross over somebody else to get there. You guys, have you guys ever heard that like that? Maybe. No, then there it is. All right. And another way to look at it is, you know, you can line it up like that. So this is not cross products because they're right on top of each other. These are cross products, so you've got to go across to get to them. Okay, cool. So some of you have heard the word cross product before, but it didn't talk about what we're actually talking about. But it's a nice connection. There's all the cross products. There they all are. We haven't used them yet. So that's what the cross product comes in and does. It uses them. So there's a little preview. That has nothing to do with the math directly behind this, by the way. This is just a demonstration of where these terms come from. How we doing? Okay. So the cross product itself is, and they start with the same example that every book starts with, torque. And when I say torque, what does that really mean? I'm kind of doing it already, but what's a torque? It's like a force, but it's a rotational force, right? It's sort of like, oh wow, I want to do a lot of physics at you, so I won't do it. But if you rotate a wrench around a nut, the actual direction the nut travels is what direction? So here's the, let's see if I can draw this pathetic picture. Here's the nut, here's my, I'm just going to give up and say that's a wrench. I'm applying a force, let's say I'm looking at it from overhead, cool? So I'm applying a force in this direction. Here's the distance from the nut to the end, right? And of course that all has to do with the fact that why we put doorknobs on the outside of doors, because if they're on the inside it'd be really hard to open the damn thing. You want to make that distance longer, and therefore your force gets multiplied by that. So, and what I just said is key. How to multiply those vectors, dot products would suck here. This is the best way to do it, isn't it? If I did my force, of course, if I put the thing on there and I started pushing directly at it, it's not going anywhere, right? Well, duh, you know, you're trying to take your tire off, you're not going to be going directly into your tire. Come on! No, dumbass. No, you got to apply it perpendicular to the damn thing. So why would dot product suck here? If this is the best way to get that thing moving, zero. Dot product would give me zero. That's stupid, right? So obviously dot product is not useful here. And what we just said also, let me see if we can get you guys to understand. If I am tightening this thing, in which case I'd be going the other way than what I just did, but let's say I'm loosening this thing. Which direction is the nut actually moving then? It's coming out, isn't it? If I'm loosening it, then it's going to be going up. If I'm tightening it, then it's going to be going down. So the direction of the actual resultant force, the rotational force, the torque, is it in the same plane as these guys? No, it's out or in, right? Okay, how we do so far? So kind of bank those ideas, what I just said. The physical requirements for this problem. Dot product sucks. the result must be itself a vector. Because it's going to have direction, isn't it? It's going to be out or in with the magnitude of something, right? And it's got to be somehow dependent on the angle. Because this is the optimal way. If my force was this, that wouldn't be the optimal way. Some of my force would have a component in, which is not doing a damn thing for me, right? You guys got it with me? Okay, maybe a little bit. Okay, so here's the idea. The torque is actually the magnitude of the cross product of these two vectors. So we still have to talk about how to. We're not even going to talk about the cross product to begin with yet, because I decided right before class that I would do it the same direction as the book does it, which is start with just the magnitude first, because that actually has a really good analogy with the dot product formula. What did we just say? This is the optimal configuration here, where the angle, of course, would be 90. So what trig function should this really be based on then? Yeah, so what this ends up being is, which looks a lot like the formula for the dot product, right? Well, why am I okay with the fact that this is a scalar? Because the cross product isn't the answer, it's the magnitude of the cross product. Be really careful, the magnitude of the cross product will of course be a scalar. You guys with me? Did this actually give me the answer of the cross product itself?
Yeah.
No, this is the formula for how long the cross product would be. Okay. I'm kind of hoping I don't have to get too deep into the explanation, because it really is just the fact that this has to be assigned so that the perpendicular situation is optimal, right? So, with that said, how the hell do you actually calculate the cross product then? We're talking about this stupid thing, but you haven't even shown us how to calculate the cross product. That's where the determinant comes in. So if I have, well, let's do this. If I have a force, oh, let's see, something not too evil. Ooh, that felt good. Let's do one out of the book here. Oh, here we go. Oh, that should be nifty. A force of 20 newtons is applied here. The R is going to be this here. I plus, which one do we do? Yeah, plus J plus here. So my OP, call it D there, but my R, my lever arm, my distance from the turning point is going to be this vector I, J, K. I, J, K. So it's going to be right there. Whoop. You can't really see it too well there, but oh well. So it's going to be I, J, K. So it's going to be like that. We'll say it. Where are we at?
What is OP?
So O is the origin, P is the point. So it's right there. So if I can blow that up, that might be a good idea. So I, J, is that cool? And K, I'm really pathetic for the purpose of showing you. Let's just overstate it. So there's my O, there's my P. I, J, K, so it's like 1, 1, 1, the point 1, 1, 1, and the vector that points to it. How are we doing? So I'm applying a force of P, and it's this at the wrench that's connected to the origin. So it's just this problem put like that. My force is in the direction 20, 0, 0. So it's not. Is it in an optimal place? Doesn't sound like it, right? Because it's only along the x-axis. So my force is going to be like this, parallel to the x-axis 20. How we do it? So that's the situation kind of drawn out. So how in the world? Let me do this two ways. Let's calculate the. torque directly, I'm sorry.
Isn't that the y-axis?
Not the y-axis.
Oh, that's the y-axis, yeah, thank you. Shoot, I was kind of hoping I could go that way because it's a little easier to see that, but oh well. There's 20. So let's do this two ways. And I actually kind of asked you to do this kind of problem on a test. I say, first use this direct formula for the torque. Then calculate the cross product, the true cross product, and find its magnitude and show they're equal. Because this is supposed to be the magnitude of what the cross product would be. So if I can find the cross product, take its magnitude, it should be the same thing as this. So let's see, the torque is defined to be F cross, and I called it D over there just because I'm used to that from physics, but R. Which is going to be the length of F, length of R, times sine theta. Now, one reason I love this kind of problem is because what is the angle between the force and that radius, that radial arm?
45.
And how do you know that?
Because it's you just step down 1 unit each direction, so it creates an equilateral triangle.
So the angle that we're going to measure is between this force that they're talking about and this radius. So it's got to be between. Of course, on the picture again, it's really hard to see, but it's got to be between the radius pointing out to this point and the force that's coming out like that. So that angle there. Who's got a good suggestion as to how to find that angle? What method do we have to find the angle between any two vectors? I don't care what dimension you're in. Dot product, right? So step 1 is to find theta. So let me attempt to see if I can ask you, can you do that? And just to help you out a little bit, what does this look like as in the same format? 1, 1. Okay. So try it out. Try to find that angle. So it's going to be in F dot R. Right? We're trying to figure out that, the angle between those two vectors. Yeah. F dot R is pretty simple, right? What is F dot R? 20, right? 20 times 1, 0, 0. So that's 20 divided by the length of F, length of R. The length of F is 20. It's amazing. Yeah, square root of 400, right? So that'll be 20 square root of 3. Inverse cosine of that would be the angle. I love it. 54.7, blah, blah, blah. And of course, this is where you just, if you got your little TI or whatever, or even if you don't, you should have like an answer button, right? So you don't have to, you can actually do the whole angle there. You can do, we already did the magnitude of F, that's 20. Magnitude of R was square root of 3 times sine of the angle. And what do we get there? You guys with me? So this is a two-step process. Number 1, I had to figure out this angle. And number 2, I had to plug the angle into the formula for the cross product. Actually, for the magnitude of the cross product. So, sorry, say it again. What do you guys get there? 28.3? Okay. And if they had the right, I don't know what units they use, but let's just say it's newtons. Right? They didn't use units, I love that. So, physics teacher would scream. So let's say it's newtons, doesn't really matter. Now, let's try to find the actual cross product and then take its magnitude. That's what we're claiming this does. We're claiming that the magnitude of the cross product is the same as this. Well, if we find the cross product and then take its magnitude, it better be that number we got there, or else the whole thing is shit. So here's how you find the cross product. Remember, I wish I wouldn't have erased this, but remember what it was. And actually, it's on page 11.4. The idea of a cross product. For example, can you guys tell me what I cross I would have to be?
1.
Careful.
0.
That'd be I dot I. I cross I would have to be 0 because
Sine 0 from 0.
sine is 0 is 0. It's a very simple answer, right? So it's the opposite of the dot product in a way, right? Dot product is maximum when they're perpendicular. I mean, minimum when they're perpendicular, maximum when they're parallel. Cross product is the opposite way. So of course J cross J would be K cross K, 0. Now I cross J is K. I love it. And that's really that whole right-hand rule. If you cross I to J, you get K, and there you go. The right-hand rule will actually point you in the direction of the answer. So here's a really good rule. I think the book does it the opposite way that I'm used to. And I don't want to change, so let's do that. I was taught this. If you go clockwise, your answer is positive. If you go J cross I, if you went J cross I, you'd actually have to point the other way, so it would be pointing down. That would be negative K. So anytime you're going clockwise, the answer is positive. I cross J is K, is positive. If you go counterclockwise, I cross K is negative J. That's a really cool little way of doing the unit vectors.
I always thought of it alphabetically.
Okay, cool. I like it. Alphabetically. So if you go counter alphabetical, sure. I never even thought about that, but that's even more direct. So that's one thing to realize, which really leads us to, if I were to do the cross product of U and V, and I really don't want to, which would be U1, U2, U3, cross with V1, V2, V3. What this really, it comes out on 715, is to be U1, V1, I cross I. Well, I cross I is 0. And so forth, which comes back to the first example I gave you. What's really going to come out of this thing? Because the next one would be, let me write this down in U1I, U2J, U3K, crossed with V1I, V2J, V3K. So U1I, V1I, those cross products die. That's already used in the dot product. I don't want it to be in the cross product. But then U1I cross V2J. What's I cross J? K. It's alphabetical, right? So I cross J is K. So this is U1, V2K. That's going to show up in the cross product. Do you really want to do that every time or memorize this thing? No, I really don't. So the shortcut to do this cross product, you do I, J, K, U1, U2, U3, V1, V2, V3. And then calculate the cross, and then calculate the determinant. That'll be the cross product. Cool? So in this case, what do I want to put in there? Specifically. So I want to do the cross product of 20 0, 0 with 1, 1, 1, right? Cross those two, are we doing okay? That would be F cross R. This will be I, J, K, 20, 0, 0, 1, 1, 1. If you put these in the wrong order, what would happen? You get the negative of what you should get, right? Because that would be just the same as reversing those. It would then be pointing in the opposite direction. Because your hand would have to curl, oops, the other way. Shit, it would be pointing in the wrong direction. So here's a beautiful thing. Which row do you want to expand around? Well, you pretty much should always do it around this, but anyone would work. If we do it around this first row, it's going to be really nice because a lot of these kind of cancel out.
You got like 2 zeros in the second.
Exactly. Yeah. So this would be, so all you really get then is, and be careful about this, that's there, so it's going to be plus, minus. So it's negative 20 times J, and that's why you don't want to do that, because that gets kind of, well, it'll still work. J minus K, right? I think that's the only one that would have anything aligned, because the other one's 0, 0, kill anything, right? How are we doing? So I ended with negative 20J plus 20K. Negative 20, yeah. 20, cool. All right, just one double check. So that's what this cross product is. Now what's the magnitude of this? Magnitude of F cross R, square root of 400 plus 400, square root of 800. You get the same thing we got over there, right? Thank the gods. Oh yeah, there's going to be a tiny difference because you might have approximated the angle, I don't know. But other than that, it should be the same. How are you feeling about that? So do you guys see the, sometimes you're just going to need the magnitude of the cross product, so then you can use the one that looks like dot product. UV sine theta instead of UV cosine theta, right? That's the magnitude of the cross product. If you need the actual cross product yourself, you've got this, which is really kind of quick, if you know your determinants.
There's 2 ways that you would get your angle.
The beautiful thing, which way, if you didn't really want to get your angle, if you didn't want to have to go through that step, you could do this instead. And then find the magnitude. They both are kind of 2-step problems, so it's a give or take. Yeah. All right, I'm getting a sense, yes?
When you go to this, when you go to the square root, that last step, you just drop the J's and the K's and everything. You just use the constants.
Well, the definition of magnitude is to take the squares of the components, add them up to square root, right? So yeah, these kind of go away. Because again, remember, this is just 0, negative 20, 20, right? So now the definition goes directly from there. Yes, just take the components. Sweet. So, I was about to say I'm getting a sense that we could use a break. So let's come back at quarter till. All right, take a little break.